So angle launching projectiles. The math on this is going to be a little trickier than what we did with horizontal, but hopefully from what you remember back in December when we did straight up and straight down, projected vertically upward problems, you will see that ultimately the math I'm going to show you is exactly the same thing. In reality, there's nothing new in this entire unit. It is simply the combination of the information that we've had in previous units. But now we're looking at angles, and so the math is a little bit different than what we did with straight horizontal launching. There's multiple cases here. So we're looking at the first case, right? And so I'm assuming that's a soccer ball. This person's kicking a soccer ball. The idea is it's going to go up and it's going to come back down and it's going to land at the same height that it started at, right? And so what that means for us is delta dy is equal to 0. That's the base problem, okay? Then the next, after today, the bulk of the notes is done for the next really 2 weeks. And so what we'll do is there's a couple special cases. There's one with that equation that's on the formula sheet that some of you tried to use for the impact angle stuff, or it's dx equals negative VO squared sine 2 theta over g. That's a special equation that pertains to these types of problems. And so we'll spend one day where I'll show you where that is useful. But that again only applies to these types of problems, this situation up here. And then the third day is, this is when dy is not equal to 0, right? Here, dy would be equal to a negative 2 meters, right? Because it lands here and it falls down. Here it equals a positive 1.5 meters. So we have an elevation change, right? And so that's the third day. We'll look at, just like we did with the vertical up and down, like the problem, the clown on the test, where he throws the thing up and he doesn't catch it, or I forget what the other problem was, but that type of idea. And ultimately, it's going to be using the quadratic formula again to solve for time, or finding the time for the ball to get to here, right? The time up, or to here, its highest point, the time up. And then from this point, right, this is, if you look at just this is horizontal projected. That's what we've just been doing, right? And then finding the time down and adding them together. So there's different ways again to do it that simply go back to stuff we've already done. So you'll hopefully make that connection and you'll be like, oh, I'm not really learning anything new. I'm just applying what I already know to a new type of problem. Now, I was searched really hard to find, well, you know, I'm a football coach. So I started with a football player and my next go-to would have been soccer, but I got so far looking with football images and things, I was trying to find a good animation of someone kicking a football. Kind of like the cannon from the physics classroom that I showed you, where it shows the projectile and Vx and Vy. And I searched a really long time, was unable to find one where it would just play while because normally in class I would be throwing an object so that way you could see it, follow that parabola, and we could talk about the velocities and all that type of thing. So I wanted something like that here, and I searched and I could not find it. I wish I knew how to make those things. That would be great, but I don't. So I kind of, it's not exactly the way I want it to go, but it's the best I could come up with. So our step one to these problems, okay, is, so remember, these are what I call the base problems. Now, in a base problem, things that are given is VO and theta, right? So we have VO, which is the original velocity, right? And we have VOX, that's the horizontal component of the original velocity. And we have VOY, which is the vertical component of the original velocity. Now, when we were doing the horizontal launching problems, the velocity given was Vox because Voy was 0. Now, that's not true anymore, right? So these, in the basic problem, this and this are going to be given. Now, there's problems where those values are not given, and that's what we'll kind of go over, those little special cases, so to speak. So these two things are given. The other thing is dy must equal 0. Okay, so whatever the projectile is, it's going to land on the same elevation that it started at. So if you kick a soccer ball on the ground, it lands back on the ground. If it kicks a football on the ground, it lands back on the ground, right? So it travels farther away from you. It doesn't go straight up and straight down. Now, again, think back to before Christmas break, right? We launched things straight up in the air. Then after Christmas break, what we just finished, we launched things, right, straight horizontally. This is our 0 degrees. This is 90 degrees, right? So we've done those two cases of projectile motion. And so now what we're doing is everything between 0 and 90, right? Which is an infinite number of values, but that doesn't mean we have an infinite number of things to learn. How we solve those problems is the same regardless of what the angle is, as long as it's between 0 and 90. So that kind of sets the stage for what we're looking at, right? And so if you were to kick a ball, right, with this velocity at this angle, I think you all know that it's going to go like this, right? And it's going to come down and land there, right? And again, we're assuming, again, I struggle to find a good picture that was big enough that you could see. He's not, if the ground is right there, obviously where his foot is, but we're assuming wherever he kicked it from, that's where it's landing, right? And so what we need to first do in step one, if we're given the initial velocity and we're given theta, is we need to find the components, Vox and Voy, right? This is going to be something that now that we're doing this with velocities, we can do this with anything that's a vector. So displacements and velocities and accelerations. And when we're done with projectile motion, we get into forces. And we do that all the time with forces. Forces is kind of like the pinnacle of, it's like if we're climbing Mount Everest, when we get through with forces, we've reached the top. And then the rest of the year is like going back down, because by then, most of you guys, if you haven't figured out how to solve physics problems now, once we're through forces, which is going to be a little bit different in terms of problem solving, everything we do after that is so much easier. So, with the forces, as you'll see, I'll break it down into the tiniest possible steps we can. But there could be some growing pains. But once we get through it, you're going to see how easy the other stuff is going to be. And you're going to look back on it and you're going to be like, man, I struggled on some stuff that don't know why I struggled, because it wasn't that hard. But it just takes a while for some of it to click. But we have to learn about what is X and Y components. And so if you're given this and you're given the angle, we need to find the X and Y component. And so this is where trig comes into play. We have the requirement of some trig, but it's the most basic possible trig. I don't know anything easier than sine, cosine, and tangent. And you guys all took like algebra 2 trig or geometry or algebra 1. I taught algebra 1. I know we did sine, cosine, tangent then. I don't know when it was first introduced, maybe in middle school. But what we're looking at, if this is the initial velocity, right, we want to break that into its X and Y component, meaning how fast is it moving horizontally and how fast is it moving vertically. Now, we talked about this when we were finding the resultant speed, right, for just what we did with the horizontal. That was the second day. And I said, well, when do we use these Vy equations? We use them to find the vertical velocity, so then we can find the resultant speed. So now what we're doing here is we're working backwards. Instead of finding the resultant speed or resultant velocity, that's this, but it's the initial. Now we're going to find the horizontal and vertical components of that initial speed, right? And so this pad that I have is getting a lot worse. I don't know why. Um, and so we make this into a right triangle, right? So again, remember this is given. We know this number and we know the angle, right? And so we want to find this and this. It's your first step in any angle problem. Now, how do we do that? Well, you have SOHCAHTOA, right? Right? Some old horse caught another horse, take oats away, or one of those devices that you guys learned. Um, I remember learning it as Chief SOHCAHTOA back in the 80s and doing some kind of um, math coloring thing where you colored in the chief based on getting answers right, right? Things that we would do in middle school. So for us, again, we need sine, cosine, and tangent. Like I talked a lot about tangent when we did the resultant speed to find the impact angle. But for this, what we want to do is look at cosine, right? Cosine of theta is the adjacent, that's the A and the H, adjacent over the hypotenuse, right? That's the relationship from trig. And then I want to solve this for VOX. That is VO times cosine of theta. This is the result that we want. Now, on a formula sheet, like if you look at the formula sheet, you're not going to see that on there because it's not a physics formula. What I will do, and I don't know if I've done it yet, is I'll make a, because even the AP formula sheet has a right triangle with some of the trig functions. And so you don't have to have that memorized. You just have to know how to apply it to what we're doing. Now, for y, it's opposite the angle. And so that is sine, right? Sine of theta is the opposite side over the hypotenuse. And so I want to solve that for VOY. That's VO times sine of theta. These are the two results. Hopefully, again, it's not that I don't ever want you to memorize anything. I want you to know how to arrive at things, from using the right triangle, geometry, and trig, and that type of thing. But you're going to do it enough times if you do the problems that you're going to remember VOX is VO cosine of theta, VOY is VO sine of theta, right? And so then it's going to be ingrained because that's what you do every time you do an angle problem. But this is the first step. We didn't have to do that before. Now remember, for physics, we always want our calculator in degrees, never radians, okay? Now, I don't know if you guys have this stuff memorized in your math class if you had to learn it, but the sine of 0 degrees, wow, this is really getting a lot worse. The sine of 0 degrees is 0, right? The sine of 90 degrees is 1. My handwriting is going to get worse because I'm trying not to rest my hand on this writing pad at all. The cosine of 0 degrees is 1. Oops, sorry, I meant the cosine. Right, the cosine of 90 is 0. So now think about what we did back, again, we did free fall, right? We spent 3 days doing free fall, 3 days roughly doing the projected upward stuff. Meaning if this, and we did a problem, if you remember, it was a battlefield punter punts the ball straight up in the air. That was, I think, one of our bell work problems or one of the problems that we did. And so, I gave you the velocity here and it was going straight up in the air, but we didn't care about X and Y because we just knew that it was only going up in the Y and coming back down in the Y. But had we thought about what we're doing now and said, well, the angle that he's kicking it is 90, and maybe this value was 50 meters per second, right? So when I plug in 50 times cosine of 90, I get 0, right? That tells me it's not going down the field. And if I put in 50 times sine of 90, sine of 90 is 1, 50 times 1 is 50. And so that tells me VOY is equal to 50, right? So we were doing it without you kind of really knowing that we were doing it back before. Yeah, I don't know, Connor. That's a good idea, actually. Except I don't have one near me. I have a hat. I'm from New York, so I have a buffalo hat, and that was every time. I'm a Tennessee Titans fan, and every time I wore a Tennessee Titans jersey or sweatshirt and watched them play this year, they lost. And so when they lost, I was like, well, I'll root for the Bills. And I got out my one Bills piece of apparel and I wore it, and they lost. So um, that's why it was sitting here, I think. But I will try that. Maybe that will help. So that's our first step. It's a new first step. Now, in terms of what happens after we do that, so the first thing we do, where's my pen? Right, is we find this VOY and we find VOX. Now, what did we say about, so a lot of the stuff, the very first day we did projectile motion, I said, what I'm telling you now holds true for the entire unit. These are like always rules. And so what did we say about horizontal motion and projectile motion? Is we said the horizontal motion is always constant. Doesn't matter what kind of problem it is, right? Oh, there goes that idea. Always constant. And so once this guy kicks the football, what are the forces that are acting on the football? Well, he kicks it to give it the initial motion, but he's not kicking it again and again and again. And so the only force acting on it, right, is the force of gravity. And in the x direction, right, we have no forces. And so once he kicks it, there's nothing to make this football go faster or slower in the x direction. And so whatever VOX is, we know that it is constant. It doesn't change. And so Vx here and at the top and right here is still the same, right? And that's exactly what we talked about with horizontal projections. Now, what did we say about the football or any object that goes straight up in the air and then comes back down? Well, eventually it has to stop, right? And so at its highest point right here, we know that Vy has to equal 0. Otherwise, it would never come back down. But Vx is still the same, right? And so the common misconception is, and I think it's because the mindset is, well, I know it stops there. It is stopping vertically, but horizontally, it's still moving away from us. So the velocity here, the resultant velocity, right? If we did Pythagorean, I can't ever say that right, Pythagorean's theorem here, this is equal to 0. The velocity is going to equal that velocity there, right? Because one of the components is 0. It's still moving, it's just not moving in the vertical direction. And so on the way up, the vertical velocity, right, is getting smaller, right? Vy is decreasing, right? And we the same notes, if you go back to your notes, like I said, this is what we talked about. Vy is decreasing, but it's a positive value because it's going up. When it reaches its highest point, it's 0. Then gravity makes it come back down and accelerates it and makes it go faster. And if we look at the football at this point right here and then straight across, it will be going the same exact velocity, but just in the opposite direction. So it'd be a negative value, right? But it's increasing because it's going down and the force of gravity is causing it to speed up. And so when it hits the ground right here, Vy here is going to be the same as Voy here. Vox here is the same everywhere, right? So it would be the same there. So if this guy kicks the football at a speed or a velocity VO of 40, meters per second, when it hits the ground, this resultant V, right, how fast it's really going using Pythagorean theorem is going to come out to be 40 also, right? And so it's looking at the fact that the horizontal velocity remains constant, the vertical velocity decreases to 0, speeds back up on the way down, all because of gravity. The only force acting on our projectile, again, because we're playing in a vacuum, right? We're playing on the moon or some other planet with no air, and we don't need air. So it's only the force of gravity. There's no other force on any projectile ever, right? So that's what happens to the velocities. Any questions on that? If I could have found a video where it launches something straight up in the air and then comes straight back down, but at the same time, it goes like this and comes back down. And so what I wanted you to see is that the vertical motion of both of these situations is exactly the same, right? Now, I was able to show to you guys when we did the horizontal launching because I showed you the video that I made, right? The two slow-mo videos that I made. I showed you the Mythbusters with dropping a bullet and firing a bullet, where an object that goes straight down or an object that goes like this, right? They hit the ground at the same time because their vertical motions are the same. That still holds true here. That you would see if we were able to launch something straight up in the air and like this, as long as the y component of this one was the same as the velocity of this one, you would see they would hit this highest point at the exact same time and come back down and hit at the exact same time. So if you remember what the graph looked like for this, that's what the graph is going to look like here. And so it starts out with some Vy value, right? Here's where it lands. Here's where it reaches its highest point, right? At 1/2 the time. Its apex, its highest point. And so we know that's a point on our graph. And then when it lands right here, whatever Vy was, it's now going to be a negative value of whatever this was. So if I come over here, there's my third point. And so then the other concept to remember is that slope of v versus t equals, right, acceleration. And so what is the acceleration of something that's a projectile? Right, the slope is equal to g, right? And again, you'll see that in your notes from, middle of December there when we did these types of problems. So again, none of this is new material. This we learned, the last 2.5 weeks, and this we learned before Christmas, but now we're combining it, right, into what we're seeing with the projectile motion now. Any questions on velocity? Velocity is the hardest part to kind of comprehend. The other parts are really kind of easy in terms of displacement and accelerations. So I kept one of the graphics, and in the pre-lesson, I had, I think, a different one. But this kind of shows you at many different points what is the velocity doing, and how we calculate Vx and Vy. And again, to remember that we can solve for this value of V at any point by simply using Pythagorean's theorem, right? I always think about it as packing and unpacking. By finding the components, we're unpacking the velocity into its x and y, but by using Pythagorean's theorem, we're packing it back together to get its real velocity. Now for displacements are easy because it's what you see, right? And so when I look at just the path of the ball, right, it's easy to see the path of the ball and talk about, well, what is it doing in terms of length, time, and distance? And so the football is going to land here. That's dx, right? That's what we call the range. And so not next class, obviously, because of what I talked about earlier, but I'm going to show you a simplified way to calculate that using that special equation. It's called the range equation. Um, but the range is just a fancy way of saying horizontal, that's an X, even though it doesn't look very good. Horizontal distance. This, right, and we solved for this before, but this is its maximum height, right? And so its elevation, its altitude, maximum height. Um, but when does that occur in terms of the path? Well, it occurs at half the total time, right? And half the total distance. So if the football goes from here to here and the guy punts the ball 50 yards away, it's going to reach its highest point at 25 yards, right? If it takes 10 seconds to land, it's going to hit its highest point here at 5 seconds. This is something that we can calculate, and we did, right? It was one of the main it was the main calculation for something that goes straight up and comes straight back down. How high did it go? And so how we calculated that value then is how we're going to calculate it now. So again, it's not going to change. And then just like we did for horizontal launching, we're going to find dx the exact same way, right? But that's what it looks like in terms of displacements, right? Much, much less concepts to kind of understand. But to make the graphs, the easy one is this, the vertical, because it's the graph looks exactly like what you see. It starts out here. Here's half the time. Well, we know that it hits its highest point at halfway. And here's the total time, and that's when it lands. And we know, again, it's accelerated motion in the vertical direction, right? And we know that accelerated motion on a distance displacement time graph means that the graph is curved. And so it looks just like that. And that's what you see it doing, right? When you see a projectile go. I know that was a great idea, but it doesn't seem to be working. So maybe try to think of another good idea. I can try. Now, so how about for dx? Well, for dx, we said that, right, this is the only equation we can use for the x direction for the entire, it doesn't matter what kind of projectile motion problem it is. It's the only equation, right? Again, that's why you can count on x. And so when we look at this, how do we solve for dx? It's vx times time. This is constant, right? And so that means the football is constantly moving away from me at a constant velocity. And so my graph, starting from here when I kick it, has to look like that, because what is the slope of a displacement time graph equal? It equals velocity, right? Which would be that value. Ignore that crazy little line right there, because what happens if I erase it? It erases the whole thing. Right, and so that's what our displacement graphs would look like. Now, probably the easiest one, because for acceleration. Now, based on what I've said, for horizontal motion, I'm trying to write on my hat now. For horizontal motion, right, the motion is, we have constant velocity. That means your acceleration is equal to 0. This is an always rule, right? There's never horizontal acceleration. Doesn't matter what kind of projectile motion problem we do. Well, what about vertical? Well, we kind of already talked about that. The motion, right, is all determined by gravity, right? The force of gravity. And so the minute we kick this football, the acceleration is always g, it's always down, and it's constant. right? And at any point, right, if there's my football, it's G and it's constant and it's down. And that's the same for any projectile motion. Doesn't have to be an angle launching. It's always the same. And so that's probably the easiest one to remember because it's the same thing we talked about before, right? And so this graph, which, maybe it would be a multiple choice question. I'm only making it a squiggly line just so you know that I'm even making something. And then for this, it's just this, right? Just like what we did when you guys did that hang time jumping activity and I made you make the sketch graphs, right? This was the sketch graph for both free fall and for up and down jumping. And it's still the same for projectile motion. It's not going to change. Any questions on any of that? So this slide has them all together, which I think I put on the pre-lesson as well. I obviously didn't make that slide. Now, some interesting, I'll call it interesting, but one of the things that I always liked to do when we used to go back when I first started teaching at Stonewall, and when I was a student teacher up in New York, we used to go a lot faster with material, and we would get to projectile motion in like October, November. And one of the labs that we would do, so it's not cold, like today it's frigid out, right? You don't want to be outside and you don't want to be launching water balloons in the weather we're having today. But that was a lab that we would do. I had these huge surgical tubings and you could put water balloons in the little pocket. I'm sure you've seen them before, and you launch them. And so you could actually launch things at angles and see what happens. Well, one of the important things about this type of problem is that 45 degrees, it's kind of like the perfect mixture of X and Y, right? The sine of 45 is 0.707. The cosine of 45 is 0.707. That's the one angle where they're the same. Well, 45 makes any projectile go the farthest distance away. You get the maximum dx value, right? The maximum range at 45, meaning if everything, as long as you keep everything else the same and all you do is adjust the angle, 45 will make it go the farthest away. So that's kind of an interesting concept that happens with angle problems. Oh, this was a 45. But the other part is when you, so I don't, this is in my way. I don't know if it's in your guys' way, the zoom bar. So this, for the 30-degree angle, here we go, and the 60-degree angle, right? So they're both, if you look at 45 being the maximum, this is 15 degrees below, this is 15 degrees above, right? 10 is 35 below, 80 is 35 above. And so what happens there is they cover the same distance, meaning these have the same dx value if they're equal above or below 45. Now, the animation, that physics classroom that I stole here from them, which I probably supposed to somehow cite, which I don't know how I would do that, but they don't do a good job of showing you that, because this, where is it? Like it lands here, but this one lands here. That they should be lined up with each other. Again, no air resistance, and you plug it in, you're going to get the same dx value. And so, depending if you were designing something or you had some kind of physics application or engineering application, you would then look and say, okay, well, I know I need the thing to land right here. So we can use 30 or 60, but is there any constraints vertically? Like maybe there's something in the way here. And so 30 degrees hits it. So you're going to pick 60 because you know that they land in the same spot, right? And so they have a different dy value. And you can see this one, the bigger angles stay in the air longer than the shorter angles, right? Because they're going to go higher, they need longer time to stop and then more time to come back down. So there are some things that are different, but the unique thing is they end up in the same exact spot. So those are concepts that are usually only addressed through a multiple choice question. All right, hold on. Oh. So this is kind of a funny video. I can't take credit for this. This is from Mr. Wesselhoff. I tried to find his webpage the other day to relink it, and I was unable to do that. But You'll see why. This goes with that monkey and the hunter problem. And he answers the question, which I thought I had this first here. A zookeeper devises a rubber band gun. So this is the more politically correct version of the one that I showed you guys before, where then I showed you the guy in the classroom, using the tin can and all that as the monkey. This is the classic question where it came from. He wants to get the monkey banana, and where does he aim? If the monkey's not going to move, does he aim above, at, or below? But if the monkey moves, does he aim above, at, or below? Well, the question is answered in this little cartoon.
Good morning, class.
Good morning, Mr.
Today I'm going to tell you a
Wonderhole.
story of how I acquired this creature for the biology department. Turn off the lights, turn on the projector. My adventure began in New York City. From there, I flew south to the jungles of the Amazon. This story is really interesting and appropriate because I had to use physics, as you'll soon learn, to capture the creature. Now, the flight was long and somewhat boring. When I finally got to the Amazon, I rented a vehicle and I drove for several hours. Wait, the natives told me that the creature I was seeking would be less aggressive if I offered it food. So I decided to hunt for something to give the creature. I soon spotted what looked like a red squirrel. I aimed above it to compensate for gravity. Physics is helpful. Finally, I spotted the creature. This time I must aim directly at the creature, since it releases its grip when it hears the noise of the gun. I successfully captured the creature, and now I can go home. Okay, turn the lights on. Let's talk about the physics. Without gravity, I would just have to aim directly at the creature to hit it. But there is gravity, and since the creature falls when it hears the gunshot, I once again aim directly at it. Bullet and creature fall together. Oh my, the creature's loose. Everyone get out of here. Oh no, oh no. Whoa, whoa. Class dismissed.
I always get a kick out of that video. It was creative, right? And so the idea would be, again, going back to what we talked about before, if there was no gravity, the monkey wouldn't fall. You'd want to aim right at the banana because the banana is not going to fall. It's going to follow a straight line, right? But because there is gravity, if you aim right at the monkey, it's still going to hit them because the banana and the monkey are both going to fall the same amount every second. And how much they fall, right, is the one. So if you look at that equation, our dy equation, that 1/2 gt squared part of the equation is how much something falls. And they're both going to fall the same amount of 1/2 gt squared every second. And so you want to aim right at the monkey still, because how far the monkey falls is the same distance that the banana falls. And it doesn't matter if you shoot it slower or faster, as this animation shows you. They shoot it a little bit slower. It just means they have more time to fall, and see it's a bigger arc, but he still catches it. He just catches it at a lower position, right? And so you want to aim right at the monkey because they're both going to fall the same amount every second. And then if you, I think I had this video on the pre-lesson, but I'll show you. And so step 2 is define time, right? Before, with horizontal launching, step 1 was define time. Then we could find our unknown. It's a game changer if time's given in the problem. It makes the problem infinitely easier. And that does happen for some of the problems, but I always I always teach you guys to or find the problems where it's kind of the middle of the road problem, because then if it's an easier problem, you're going to know how to do it anyway. And so for us, step 2 is define time. If Vx and Dx are given, then you want to use this equation to find time. It's always the easiest way to go. And it's exactly what we did when we did the horizontal launching problems. Again, X never changes for us, right? That's what makes it nice and consistent. So if Dx and Vx are given, use that to find time. Well, it's not always the case that it is, right? And so then we look at the Y equation to find time. And so when we were doing horizontal launching, this was equal to 0, right? But now that's not equal to 0, right? VOY is equal to VO sine of theta. That goes there. So it's not 0. But for the base problem, this is 0, right? And so now we have 0 equals, sorry, that equals t plus 1/2 gt squared. And we want to solve that for time, but I have a t squared and a t, so what can I do? Well, I always use the F word that we can actually use and not get in trouble, and that is factoring. It means get rid of a t, because then it becomes, oops, sorry, not that, right? And now if I solve this for t, it means bring this over, multiply by 2, divide by g, right? I get this result. Now, if you think back to what we did with straight up and down motion, I showed you 3 different ways to solve for time, and this was one of them where we did this, right? And it came from the same equation, making this 0, and it was the exact same math, right? But I actually showed you 3 different ways to solve for time, and all 3 ways, this being one of them, work in this problem as well, because you can use this equation. Wow, it's really getting bad now. And it just depends on what you decide to make this. If you make this 0, right, we solved for the time up only. Or if this is 10, you make this -10 and it gives you the total time. But that process still works. And again, we'll go back over this on Wednesday. And then the other way to find time was, well, using this equation. Sorry, was what I was going to write. I forgot I had made the slide, right? We can use this equation, and we can use it 2 ways. We can either make Vy equal to 0 at the top, and that gives me, right, half the time or time up, or we make Vy equal and opposite to Vo, and it gives me the total time. And I'll go over that in a little more detail on Wednesday, because I just want to show you the other step, and that is to find the maximum height. And you can use this equation to do that, but the key to that is you can't, right, if you're trying to find how high something goes right here, and you've solved for time to be 10 seconds, and you put in 10 seconds here and here, you're going to get 0, because you've solved for the time for it to be here. So you have to remember to use half of the total time, right? That's the mistake that people make when they use that equation, is making sure you put in half the time. And then the other mistake that people make is they forget to make this a -10, right? If you don't make it a negative, you're obviously gonna make this thing end up way up here. That doesn't happen. And again, just like with time, there's another way to solve for that, and this was our go-to version of solving for the height, right? We know if something goes up and comes back down at this point, the Vy value is equal to 0. So it's the same as if it does this, as we talked about earlier. If I make this equal to 0, and I solve for dy, right? I'm going to subtract this over, and then I'm going to divide by 2g. I'm going to have to look into purchasing a new pad, I guess. Right? If you remember what we did when we did the straight up and down problems, we had this. We didn't have to add y's because we weren't doing two-dimensional motion. And so it's the same, it's the exact same math again. And then the last thing is, how do we solve for dx, right? If we didn't use the x equation to solve for time, well, then we do that. Same thing we did before with horizontal projection. And we use the total time to find dx always.